12 million vehicles are dismantled and recycled annually in the United States alone. This volume turns ordinary scrapyards into some of the most efficient steel mines humanity has ever created. One can notice how mountains of discarded metal accumulate, waiting for processing into a new resource. Why does the global market rely so heavily on this specific source, rather than traditional mines? At first glance, it seems that extracting ore is the only path to obtaining steel, but geological mining involves immense energy costs. In reality, the auto recycling industry, often called the car's second gateway, delivers a massive stream of prepared metal every year. But this is just the beginning. Each car embarks on a new journey immediately after dismantling. It is visible how the scrap is transformed into the raw foundation for construction, heavy industry, and even the next generation of automobiles. Thus, the material transitions from a finished product back into an essential resource without haste. $48,000 is the initial price of a car that spends 10 years on the road. How much value can it still hold once it enters the recycling process? At first glance, a rusted vehicle seems like worthless waste, but in reality, behind that question lies a $60 billion industry operating every year. Millions of old vehicles are dismantled, crushed, and reborn as new raw materials. This massive sector provides jobs for hundreds of thousands of workers globally. But this is just the beginning. If iron ore is a natural mine, then end-of-life cars represent an artificial mine without limits. Because processing scrap cuts enormous costs for metal smelting compared to raw extraction. Each recycling cycle saves up to 74% of the energy compared to mining new ore. This greatly reduces the industrial burden on the environment. Automated lines recover on average 75% of a vehicle's weight. One can notice how the equipment sorts everything from steel and aluminum to glass and plastics. Hundreds of millions of tons of material are reborn every year. It does not end at this stage. Consequently, the refined material continues its journey as buildings, everyday products, and the next generation of cars. 95% of end-of-life vehicles in the United States pass through this exact system. This makes the automobile the most recycled consumer product in the world, eventually transforming into everyday products or even the next generation of cars. When a car reaches the end of its life, it is delivered to the intake area of a recycling plant. One can notice the steady stream of arrivals at the gate. But this is just the beginning. Technicians immediately record the vehicle identification number and engine number. Why is it necessary to document the year of manufacture and overall condition with such precision? A simple head count would seem sufficient. This data, including related paperwork, provides the basis for assessing the remaining value of each vehicle within the digital management system. Workers photograph the car and attach a unique tracking code to the chassis. This step allows the entire process to be tracked. The inspection focuses intently on components that can be reused, such as engines, transmissions, electronics, and interior parts. Usable components are separated and supplied to the multi-billion-dollar market for used auto parts. It gets more complex further on. Vehicles that are heavily damaged or fully worn out face a different trajectory. At first glance, these units seem like waste, but in reality, they are directed straight into the dismantling process for material recovery. The metal awaits the next operation. Once this stage is complete, the cars are organized in lots across the yard. The camera glides along the rows where vehicles stand lined up, ready to enter the processing line in a clear, systematic order. Thanks to this level of organization, every car is able to maximize its recoverable value and contribute back to the economy. The workflow proceeds to the next stage without delay. 98% is the recycling rate reached by standard lead-acid batteries, a figure that sets the standard for efficiency in this facility. the vehicle maximizes its recoverable value and contributes back to the economy after intake. And inspection are fully complete. Once moved into the processing area, the first step is removing the battery, which represents the most dangerous electrical risk still present. In conventional gasoline cars, this unit is removed immediately, since the lead, plastic, and even the sulfuric acid inside can all be recovered to make new batteries. However, for hybrids or electric vehicles, the process demands strictly controlled caution. Technicians adhere to a much stricter procedure when handling the large lithium-ion packs found in modern chassis. Why do these specific components require such complex handling protocols compared to standard units? Mere extraction is not enough given the high voltage systems involved. They are carefully detached, safely packaged, and sent to specialized recycling facilities before the vehicle is cleared to move on to the next stages. One can notice how the car is lifted onto a platform where hydraulic clamps secure the frame in place for fluid extraction. A specialized steel probe pierces the tank and connects to a high-pressure vacuum pump to begin the withdrawal. At first glance, it looks like a simple draining operation, but in reality, it meticulously captures gasoline, engine oil, transmission fluid, brake fluid, coolant, and even refrigerant gas from the air conditioning. On average, an end-of-life vehicle still contains several gallons of fuel and fluids, enough to cause fires, explosions, or pollution if not handled correctly. Within minutes, everything is drained and directed into underground reservoirs. But this is just the beginning of the efficiency cycle. What makes this step notable is that nothing goes to waste in the recovery chain. Once filtered, most of the recovered fluids are reused to power forklifts, generators, and other equipment inside the plant. It is visible how pressure sensors, one-way valves, and sealing caps maintain a completely closed system to prevent vapors from escaping. The remainder is stored for in-house operations, helping to significantly cut energy costs while ensuring safety for the entire line. The drained chassis is now prepared for the subsequent mechanical processing. Tens of major components must be stripped from the vehicle to ensure safety for the entire processing line. Once all the fluids have been drained, the car moves into the stage of dismantling its heavy parts. Wheels are usually removed first since they take up significant space and are easy to process. Old tires are among the most difficult types of waste, taking decades to decompose if sent to landfills. Instead, most are shredded into rubber granules for asphalt roads, while others are used as alternative fuel in industrial furnaces. But this is just the beginning. The steel and aluminum rims are separated immediately. They are sent directly to smelters for metal recycling. Why are windshields cut out with specialized equipment? The glass seems brittle and easy to crush along with the frame. However, these are laminated sheets reinforced with a PVB layer that prevents shattering. Recycling recovers not only the glass shards, but also the PVB layer, which is reused in soundproofing materials and industrial coatings. Then the doors are removed from the body. At first glance, a door seems like a simple single piece, but in reality, it combines multiple distinct materials. The steel or aluminum frames are cut away for remelting. Electric motors for window controls and locking systems are stripped to recover copper and magnets. The interior follows with seats, dashboards, and carpets carefully dismantled. It is visible how workers strip wiring to retrieve the copper core, while plastics and fabrics are shredded and repurposed into new materials. It gets more complex further on. Finally, the engine and transmission are hoisted out. These are the heaviest and most valuable mechanical assemblies in the vehicle. Some units are refurbished for resale, while others are broken down further to extract aluminum, steel, and copper. Even precious metals are recovered from catalytic converters. This systematic sequence maximizes the remaining value of each component, while also ensuring that the next step can proceed safely. the process transitions to the crushing of the vehicle's frame. Before a car enters the crusher, it still carries a mix of non-metallic parts that are difficult to process, from bent exhaust pipes to tangled wiring. To remove them, the vehicle is sent to the rough processing area. Massive mechanical arms fitted with hydraulic shears take over the job. With tens of tons of clamping force, the steel jaws rip off any remaining doors, yank out exhaust systems, or crush radiators in seconds. One can notice how the machine discards plastics and foam padding that cannot be smelted on the spot. And this is not the limit. Thanks to sheer mechanical power, the car's frame is quickly stripped clean of unwanted parts, far faster than manual disassembly. This cleaning step acts as a coarse filter for the entire line, eliminating materials that could ignite, contaminate the recovered metal, or damage the crusher itself. After only a few minutes under the hydraulic shear, the vehicle's structure is reduced to a neat steel and aluminum shell. The frame is ready for compaction with maximum efficiency and safety. 150 to 200 tons of crushing force descend upon the bare steel frame to maximize efficiency. The massive hydraulic press activates, compressing a structure more than 4 meters long into a compact block of metal, reducing its volume to just a tenth. Why does the industry rely on several distinct technologies for this single task? The objective of compaction appears identical in every scenario, but in reality, each machine is designed with a specific purpose to optimize logistics and energy consumption. The car baler forces the frame into a dense, cube-shaped steel bale. These high-density blocks are easy to stack and transport between facilities. Modern industrial balers handle 25 to 40 cars per hour, making them ideal for large-scale operations requiring efficient storage before shredding. But this is just the beginning of the process. In contrast, the car flattener finds popularity in mid-sized or smaller scrapyards where speed is paramount. It compresses vehicles into flat sheets only a few dozen centimeters thick, prioritizing lower energy use and investment costs. One can notice how the machine simply rolls the metal thin rather than boxing it, though these sheets are less dense than bales and require more energy to shred later. Meanwhile, the shear baler simultaneously compresses and slices the vehicle into short, manageable sections. Consequently, although its throughput is lower, it offers a direct path to shredders or even directly into smelters, skipping the baling step entirely. Baling resembles packing goods tightly. Flattening is like rolling them thin, and shearing is akin to chopping them into ready-made pieces. It gets more complex further on. 100 to 150 tons of steel per hour pass through the mechanical heart of the line, the high-capacity shredder. Inside its chamber, massive steel shafts with interlocking teeth rotate in opposite directions, tearing the compressed block apart within seconds. It is visible how the metal buckles and snaps under the immense torque, filling the air with a thunderous clash as the car turns into uniform fragments. This sheer efficiency allows the auto recycling industry to operate at a staggering scale. The mix of metals and non-metals is carried along a sorting line where powerful magnets pull out carbon steel first. One can observe how eddy currents deflect aluminum and copper to the side, while plastics, rubber, and fabric residues are discarded. Everything only gets more complicated. As a result, the recovered steel is compressed into bundles for the furnace, while non-ferrous metals are collected separately for other industries. From a single discarded car, the line takes less than 1 hour to recover pure reusable metals. The material is now fully prepared to re-enter the cycle of production without delay. Tens of thousands of amps unleash a blazing arc like artificial lightning the moment graphite electrodes descend into the electric arc furnace. Why subject the compacted steel bales to such an immediate inferno? These blocks, composed of shredded and sorted old car frames, are dense and cold. Without the sudden shock of extreme heat, The melting process would be inefficient and the mixture uneven. The temperature soars beyond 1,600 degrees Celsius within minutes, turning the scrap red hot. One can notice how the solid metal collapses into a glowing liquid pool under the intense energy. Lime and flux are introduced to the melt to draw out impurities, while oxygen lances burn away unwanted elements with a fierce intensity. A layer of slag forms on the surface, separating from the pure alloy below. Sensors and spectrographic analysis provide continuous monitoring, ensuring the composition meets exact specifications. But this is just the beginning. At first glance, the furnace interior looks like a chaotic mass of fire, but in reality, a glowing sea of pure molten steel is emerging for casting. The refined metal flows through sealed troughs into the continuous casting line without delay. Water-cooled molds receive the blazing stream, solidifying the outer shell within seconds, while the core remains molten. Because the center of the strand is still liquid, motorized rollers carry the material forward to cool gradually along the length of the line. Long billets stretching tens of meters take shape, destined to become square construction steel or flat slabs for rolling. Automated thermal saws cut them into standard segments, each weighing several tons. Every billet is numbered, scanned, and logged into batches. From a formless pool, defined blocks of material now exist. It is visible how the glowing red billets surge into the hot rolling mill immediately after leaving the reheating furnace. Dozens of massive rollers continuously press, stretch, and bend the material into new shapes. With every pass, the heavy, rough block flattens and lengthens into uniform sheets or coils. High-speed cameras and laser sensors monitor thickness and straightness every millisecond. The process is only gaining momentum. Freshly rolled steel cannot be sent out immediately and requires a controlled drop in temperature. High-pressure spray nozzles envelop the surface in a white mist, rapidly cooling the metal without causing cracks. Powerful fans blow along the length of the coils, allowing the steel to preserve its internal structure through gradual thermal reduction. Therefore, every coil undergoes a rigorous final inspection before it can be stamped and stored. Ultrasonic sensors scan for hidden fractures deep inside the material, while mechanical testers measure tensile strength. High-resolution cameras examine every surface detail to ensure quality. From fiery brilliance to stable strength, the steel is now ready to serve hundreds of modern industries. Hundreds of tons of force are exerted by massive presses, crushing the chassis of what was once a functional vehicle. The process actually begins earlier with the dismantling of every reusable part and the draining of fuel to guarantee safety. One can notice how the hydraulic rams compress the metal frame into a compact block. But this is just the beginning. Why does the material undergo such intense fragmentation in the next stage? The shredder engages, tearing the compressed metal apart with a thunderous roar. This mechanical violence is necessary to expose the different materials for the sorting phase. At first glance, the shredder output appears to be a chaotic pile of waste. But in reality, it is a valuable resource stream sorted by advanced technology. One can observe how magnets lift ferrous metals while eddy currents eject non-ferrous pieces from the belt. It is visible how the sensors identify materials before they enter the furnace to be reborn. The molten steel is then hot-rolled, cooled, and rigorously inspected. Everything only gets more complicated. This cycle fuels a multi-billion-dollar industry that significantly cuts energy consumption. Instead of straining natural resources, the end-of-life vehicle transforms into clean, durable material. One can see the finished steel surfaces as they are prepared for vital industries like construction, machinery, or the creation of new automobiles. The metal is ready for its next application in the modern economy.